Hi, welcome everybody. Can you hear me okay? No. Okay, let's try the mic. Maybe I got to turn it on. No, it's on. Hello, testing 01. Testing. Can anybody hear me now? Raise your hand if you can't hear me. How did you? Okay, well, you know, I'm not sure. I could shout, but let's hope the mic is picking it up. Is it okay, Jason?
The speakers are on, but they're just making a humming noise.
And it's drowning you out.
Oh.
The humming noise from the speakers is not.
The humming. Oh, okay. All right. Well, let's fix that before we go. Okay. So somebody's working on the hum. I got a beautiful. I got a beautiful blue glow on that monitor there too. I don't know. Okay. So meanwhile, I better not even try to talk if you can't hear me, right? Now, is it better? Hello? No, not better. Okay, well, I'll fix it up. While they're waiting to figure that out, let me just say, are there any Stanford students who might be interested on a project without funding this summer that might take a week on math problem? Have any? Okay, well.
I'm not a student,
maybe in the what?
I'm not a student, but I'll be happy to.
You'll be happy to do it. You're not a student, yeah. Okay, so I'll maybe talk about it a little bit. Is the audio working now?
You may want to move up the mic.
Here we go. I see. Plan B. Okay, he says it might be loud at first, but he will bring it down. Thank you, Jason. Okay, welcome to this talk, which you can see from the title, is called Knuths Graph. And I guess that one of the main reasons I'm doing it here is to celebrate that I finally hello. Welcome to Computer Musings and to Stanford University, the Center of Audio Technology. And the reason that I wanted to give this talk today is partly selfish. I like to celebrate the fact that I finally know what the first 46 pages of Volume 4 of the Art of Computer Programming are going to look like. At least almost everything. It's a project that I started in 1962, and actually I still have another 2 inches on page 46 that I might think of something to put on there, but even if it's left blank, it'll be okay. Anyway, let's put it up on the screen. You can download it very easily if you go to my home page. And then go to the news page. At the top of the news page, it tells you how to get preprints. Jason, can you put this on? Can you focus on this? Here we go. Right. So at the top of the news page, it'll tell you how to get pre-fascicle 0A. And there's also 0B, 0C, and 1A that are available now. These I know we got a lot of Google people here in the first couple of rows, and you can also, I don't know, it used to be that you could get to my home page just by typing Don, but that's not true anymore. So if you guys can do anything about that, I'd appreciate it. But I noticed that Google already has scanned the text of this, and sentences inside of this are appearing already in the search, so that's pretty impressive. Since I just put this online a couple of weeks ago. Now, I guess I might as well give a little look ahead. already on volume 4 there are these paperback things that, called fascicles, 2, 3, and 4, which are approximately, things that come in the middle of volume 4, and there's going to be, I don't know, probably dozens of these altogether, because volume 4 is going to be, God willing, it's going to be volume 4A, B, and C, and I'm not sure how much further, but I don't think there'll be a Z. So it'll, but anyway, there's a lot of stuff to say in there, but I couldn't really write the beginning first. If you're a computer programmer, you write the initialization last. It's a little bit hard to say what you need to bootstrap the whole thing. So first I got these done, and these are available and translated already into several languages, and now in the fall, we're going to publish 0, fascicle 0, and what's available online is the pre-fascicle, which is otherwise known as beta testing, and this is your chance to look at this material before too many other people have seen it, because I pay good money for anybody who finds errors in the text, unless somebody else found the error first. And for example, while I was preparing for today, I noticed an error on page 30. So you could have, yesterday you could have found it and told me about it and made $2.56. But today I already know that one. And I don't like to be the one who catches these errors. I like to hope that somebody else is actually reading this stuff. But anyway, the pre-fascicles 0, A, B, and C are going to go together into fascicle 0, and that should come out October, November, something like that. Now, I've also got pre-fascicle 1A on the web, and that is even cooler than cool graphs, I have to say. It's all about, it's called Bitwise Tricks and Techniques, and it collects the folklore that I've learned over the years about how to make use of the instructions that most computers have, but people think are only good for one or two things. And right now I'm having a ball writing pre-fascicle 1B, which I think I should get done in 2-3 months, which is about representing Boolean functions, and it's I don't know. Yesterday I invented what might be a new, anyway, really interesting data structure, and I'm having a lot of fun writing that part. So then the plan is that 1A and 1B will be put together into fascicle 1 early next year. So then we'll have 0, 1, 2, 3, and 4. But that'll be, I don't know, 500 pages or so, but it's still not enough to put out into a hardback. So then I'm going to get a couple. I'm going to finish up a couple other book projects, and then come back and do fascicle 5, maybe 6, and then we'll come out with a real hard cover. So it'll be a while, but if you can see the shirt I'm wearing, it says Art of Computer Programming Volume 4. That my wife made this shirt for me as a joke some I don't know, maybe 20 years ago, and I wear it every time I can report a little bit of progress on the project. Okay, now. So if you were, okay, so this is an introduction to combinatorial searching, which is the main topic of Volume 4, and one of the most important things in combinatorial algorithms is algorithms that work on graphs, because graphs are everywhere in applications, and the most somehow in many ways the most versatile of all the combinatorial structures. So naturally, I also this is largely an introduction to graphs. If you were writing a book that was introduction to graphs, well, try to think what you would do. You have to of course, give a whole bunch of definitions and explain the basic things about graphs. And one of the main things that you would probably do is try to have a lot of cool examples. And then so in these 46 pages, plus answers to the exercises, which take you up to 67 pages, in these pages, I've got an introduction to graph theory that also I think has a lot of interesting examples, and a few algorithms that don't go into graph algorithms per se, but into specific topics on graphs, like how to find a maximum matching or something like this. But instead, graphs algorithms that are sort of close to the definitions in some sense that help to reinforce the whole idea of what graphs are. Now, let me show you then a few of the illustrations in here, and that before I get into the main thing I wanted to discuss today, which is one of these algorithms that I got excited about as I was writing. Okay, well, I actually don't get to graphs and shit. I mean, I start talking about playing cards and other kind of combinatorial things for a while, but I do finally get to graphs on page 13, Graph Theory: The Basics, and on page 14 you can see here's some pictures. So Jason, can we get a close-up of this where I'm pointing here? Hello, Jason? Yeah, good. So I'm going to be doing this a lot. I'm going to be pointing to the book a lot. You don't want to watch me, you just want to watch the book. Here are examples of maybe some of the most important graphs of small size. So for example, a graph with 10 vertices, the Peterson graph has to be the winner of the most interesting graph of this kind. It's been used over the years to serve as counterexamples for almost every conjecture that somebody had that isn't really true about graphs. Usually it starts out, the smallest counterexample is the Peterson graph, and even Peterson, when he first published it, he was giving a counterexample to somebody else's conjecture. And there's a whole book written about the Peterson graph. The most important graph on 8 vertices is probably the 3 cube shown here. Graphs can be drawn in many different ways. All of these graphs down here are also the same as the 3 cube. Exactly the same graph, but different ways to present it, show you different things about it. Now, the one up here in the corner, Schwartal graph, is my vote for the most interesting graph on 12 vertices, and we can talk a little bit more about that later. Now Vasek Schwartal was a professor here at Stanford during the 70s, and one of the best in graph theory. He's gone on to do many other kinds of mathematics as well, and is now at Concordia University in Montreal, which is his favorite city. He always was in love with Montreal even when he was at Stanford, so we were lucky to get him here for almost 10 years. Now, but if you go to his home page, you find that he has a picture of this graph on 12 vertices, which he published in the 70s, in the early 70s. And the reason was, well, it's the smallest graph that has several properties that I can describe in a minute. And on his homepage, he still draws the graph this way. But when I wrote to him and asked him more of the story of the graph, he said, his friend Adrian Bondry has just found a new way to draw this graph that shows more of its symmetries. And so this is the way Adrian Bondry draws Vasek's graph. I think if you study it a little while, you'll see that it actually is cool. Now, Vasek's homepage also has a whole bunch of other stuff that's easy to read, but so sometime if you want to see some more stuff. But okay, let's see. I thought that
what is its original claim to fame? And I'll just state it, not prove it, just so you get the idea. Maybe I better look it up in the index if I'm going to find it. There's an index at the back. You get $2.56 for every error in the index. If something isn't in the index, should be, I pay. Got to get this book right. So his graph, it's discussed on page 12
14, 39, 44, and 62. So let's look on page 39. It says somewhere, Spatow's graph. How many symmetries does Spatow's graph have? Okay, so you can say how many ways are there to permute the vertices, and so that the edges stay the same. So you renumber the vertices so that every vertex v goes instead to f of v, and then you have f of v is adjacent to f of u if and only if u and v were adjacent to each other in the original graph. How many symmetries does it have? Okay, so that's an exercise there. That's on page. That was on page 39. What about page 44? Here's where we get to the reason that he really discussed it, and that is to ask about coloring it. So the minimum number of colors that you need to color this graph, and it also it also turns out to be a okay. So I'll get the picture of the graph on the screen again, and you have to convince yourself that you can't color that with 3 colors. And then if you look at the answer to exercise 124, by the way, it's allowed to look at the answers, but you're first supposed to think about the exercise. And so there's a proof on answer 124 why you need 4 colors for it, and then, but this is an illustration about what's called the girth of a graph. Now, the girth of a graph is the length of the smallest cycle. So you see, there's no 3 cycles in this graph. There's no triangles. But there's a cycle of length. There's lots of cycles of length 4. You can go around like that, a square. So this is a graph that happens to need 4 colors to color it, and it has girth 4, and it also every vertex has exactly 4 neighbors. So it's a regular graph also of degree 4, and it wasn't easy to find a graph that was regular degree 4. It needed 4 colors and also had girth 4. Now, there's a famous unsolved problem in graph theory. Some are more famous than others, but this one is one of the better, one of the winners. I got to make sure I don't get my. And that is it's called Grunbaum's conjecture, and Grunbaum found one that had girth 5. Now, a man in Germany named Brinkmann, who I contacted by email, he showed that there's a graph of 21 vertices, and it has it's 4 regular, 4 colorable, and the smallest cycle is length 5, and nobody knows if there's one that has girth 6 or 7 or something. Although Grunbaum conjectured that you could do this for all larger and larger girths, and computer search has been done up to 34 vertices to find one of girth more than 5, but there aren't any. So you've got to have at least 35 vertices if you're going to win that one. Now, anyway, so that's Spatow's graph. The graph that I think is most fun of all, actually, in the whole business is the graph based on words of English. So it's not so mathematical as this. It's not regular. It's not got any of this other stuff. But instead, it's based on what I consider all the 5-letter words of the English language. Now, for 20 years, I went and made my personal collection of 5-letter words. Just because a word is in the dictionary doesn't mean to me that's a word. It's no fun if you're playing Scrabble against somebody who just has a bigger dictionary than you and comes up with these things. To me, it's if I'm going to use it in an example, it should be a word that I believe is a word that somehow I see somehow. And so I spent several hours interviewing my daughter, asking her how many 5-letter words she knew. I also made statistics so I could figure out which words are more common than others. And for years and years, I went saying, I wonder if this is in my list. And I checked it against, of course, the various dictionaries to get going. And there was a famous dictionary called the Jotto Dictionary that we had on one of the first ones in early days of computers. And anyway, 5-letter words turn out to be more interesting than 4-letter words and 6-letter words, but I don't have time to go into all the details about that. But anyway, I came up with what I considered a complete set, and then it was time to freeze the set and say, from now on, I'm never going to change this anymore. I'm going to say these are the words as they existed in a certain data set, which is now fixed for all time, and it's not going to so that I don't have to worry about continuing to update my book or anything else whenever it changes. Now these words are all part of something called the Stanford Graph base. I gave a lecture, a computer using lecture about this maybe 10, 12 years ago, and this book it's still in print, but the shelves are flat. So if anybody wants to suggest something to your parents, as to what would be a great present to have, I mean it's a fairly fun read. This book contains 3 dozen short algorithms that work on graphs, presented as examples of literate programs, and also has a lot of nice pictures, etc. And it includes at the end the most common 3,000 5-letter words of English as an appendix. So you can see them. You can see them here. Can you bring them up here? Okay, so aback is number 2476. Abate 2877. Okay, about 4. Above 49. So each one has a ranking from 1 to 3,000. Actually, the total number of 5-letter words of English, according to me, is 5757. But I don't give all of them here because I didn't expurgate the. Some 5-letter words are plurals of 4-letter words, and so you might it might be embarrassing to have them on television. But the first 3 most common 3,000 are pretty safe. So they're in here. Now, but if you think of a 5-letter word that you might think is a little bit risque, you can still look it up in the database. Now, why does this have to do with graphs and crude graphs? Well, it's because there's a Lewis Carroll invented a game at the end of 1877 based on changing one word into another by changing one letter at a time. Do people know this? It's often called word ladders or laddergrams or something like that. And so, for example, here's one of his examples. He changed tears into smiles. Tears, sears, stars, stare, stale, style, smile. Okay. So here we have a graph. 5,757 vertices. Two of them are adjacent. If you only need to change one letter in the same position. This graph has lots of neat properties, and so almost every algorithm that I'm going to do on graphs throughout Volume 4, I'm going to have various ways to tie this in with the graph of all 5-letter words and try the algorithm out on that graph and see what can happen. For example, right now I'm just writing classical. I'm just writing about BDDs, like data structure for Boolean functions, and I decided to take these 57 words and consider them to be a function of 25 Boolean variables because you can encode each letter as in 5 bits, and so you have 25 bits, and then you say is this pattern a five-letter word or not? And I just I just found out that it was only about 6,500 nodes in the ordered decision diagram for this data structure. Anyway, so I can find lots and lots of examples of how to use these words in graphs and also in other ways. Now the graph. Hello. Yeah. That's a very good question. But when you ask a question, there's a microphone in front of you, and you're supposed to press the red button.
Is the set fully connected, which is to say...
Is it fully connected? Can you get from any word to any other?
Yes.
In fact, no. Okay, so there's a demonstration program. You can download it from my website, and you can run it, and it'll give you the shortest thing here. So, for example, here's an example. You say you ask for words, and you try to convert that into a graph, right? So, okay, words, wolves, goals, graphs. There you go. Ask for another starting word. Flour to bread. Okay. Chaos to order. Okay. Pound to euros. Can't do it. Okay. Now it turns out that there's two reasons why this is true. You can't change anything into euros. There's no word adjacent to euros. It's an isolated vertex. And the second reason is that pound is a member of this small, rather large component, but you can't break out of it. You can get pound, hound, round, bound, found, sound, wound, wood, world. You can get to court, fount, and so on. But this is it. Okay, so it's not connected. But there's a giant component so the giant component has 4,493 words in it. From any of these, you can get to any of the others. And I discuss in here a quick. Usually, like if you can get 2 steps away from your starting word and 2 steps away from the back word, then your chances are something like 96% that you're in the giant component. But pound is one of the exceptions.
So how many sets are there?
So by the way, what the question is?
How many disjoint sets are there?
Yeah, that's all answered in this book. For example, there are some components of size 2 that just 2 words, and some of them are kind of cute, like droid and druid. Alpha, aloha. Okay. But then you can't break out of those. But anyway, lots of fun with this, and not only for shortest path algorithm, but it makes a great demo of different kinds of shortest path algorithms to convert one to another. But here, for example, there's people work on graphs. They have something called the Steiner tree problem, where you try to find the shortest way to connect several vertices. And here I took blood, sweat, and tears. Blood, sweat, and tears, and then with these connections, this is the shortest way to connect those three words. On the cover of this, I connect benchmarks, with a Steiner tree. Okay, so you can work on lots of
your graph algorithms and on a fairly good-sized graph that people can intuit what it means, and you can illustrate the graph. So I think that's a lot of fun. Now, another interesting one that I have here is the graph is based on the United States. Let's see, that's on page 15. What happened here? I see I switched the page. Okay. So these are the what used to be called the continental United States, now the contiguous United States, and I also added the District of Columbia. So this is Delaware, this is D.C. here. And so this is an example, of course, of a planar graph. And it has 107 edges. I know that because I had to draw this darn thing, and I had to lay it out on the page. And I had to make the, all the illustrations in my book are generated by MetaPost, and it's a lot of fun to use that program. But I also have to
add a line in the code. So as I was doing this, putting in all these 107 edges between states, it was really a wonderful nostalgic trip for me, because I could remember different times in my life when I drove between these two states. California to Oregon. Oh yeah, I did, California to Nevada, Nevada, Oregon to Washington, Washington to Idaho. Once I went Idaho to Montana. I went Wisconsin to Michigan to Ohio. All these things, almost all of these I could remember at some point in my life driving there. So anyway, I have to consider this a cool graph. Also, I got an illustration of on this graph of the so-called maximum independent set algorithm. Let's see. Okay, that comes in here. Yeah. So you see, an independent set as a graph is where you choose vertices, but no two are next to each other. And so here is a maximal independent set, means that I can't add any more. I can't add California here because it's next to this guy down here, which must be Arizona. So I can't, so everything that I haven't colored in is next to one of the ones I've colored in. So it's a maximal independent set that has 12 vertices. So the ones that aren't colored in, that's called a vertex cover, and it's a minimal vertex cover with 49 minus 12 vertices. But actually, to get a minimum vertex cover and a maximum independent set, you can actually find 19 states that have no, that are mutually, you can't drive from one to the other. And so lots of graph algorithms, of course, can be demonstrated on these graphs. And some of the graphs have mathematical structure, like Schwartal's graph, but some of them have an organic, real-world structure, like 5-letter words or the graph of the United States. Now, there's also oriented or directed graphs, and here I haven't really found much to do with algorithms, but I wanted to present it because this is a graph that appears in Agatha Christie's novel Murder on the Orient Express, and this graph was actually given by Hercule Poirot as he's trying to solve a mystery, and the different vertices here are the characters in the novel, and you have an arrow if one has an alibi for the other. And so he's summarizing the status of the mystery, and this is the graph that he describes in that. I'm still looking for a reason to use this in an algorithm, but I had to put it in the book anyway because I thought it was cool. Now, the Stanford graph base has not only algorithms but graphs in it that are intended for use in experiments. And I worked with a lot of Stanford students to prepare this some 20 years ago. And not only the 5-letter words, but several others that I'm going to show you in the next few minutes are in there. It's also, there's a whole set of software tools that go with this so that you can easily be sure that you're getting exactly the graphs. They're carefully sum checked so that no mistakes have been made, and then lots of ways to combine these graphs to make many other graphs from the ones that are given. There are lots of graph libraries and programs available, but they all seem to be proprietary and cost money. This is free; you can download it, and it's all. And I'm going to base zillions of examples on these graphs. So I went to a lot of trouble to make this whole thing easily available. Now, let me show you then just a few of these. First of all, there's a graph based on Roget's thesaurus. The original Roget's thesaurus from the 19th century by Pierre Marc Roget and his son, and Stanford students helped me to key in all this data. So this has 1022 vertices, and then there's this is a directed graph, so there's an arc from one. There's the concepts that are in the thesaurus. So there's an arc from water to moisture, and an arc from discovery to truth. An arc from vulgarity to ugliness, and so on. All of these are examples. So when there's a cross-reference under one topic, one general topic to another, you're looking up water and says see also moisture. Then that gives you a directed graph with some interesting structure. Then there are graphs based on literature, several novels and other books like the Iliad. Or is it the Odyssey? One of those two. It's one of Homer's two things. Anyway, this is Jean Valjean. This is Les Miserables, a graph where the vertices are the characters of the novel, and the edges are characters who encounter each other somewhere. And then there's also a bipartite graph, which has one vertex for every character and one vertex for every chapter of the book, and then if a certain character appeared in that chapter, then you get an edge in the graph. That's an example of a bipartite graph that you can use for testing algorithms on bipartite. Now, I've got Mona Lisa in there. I've got a digitized version of Mona Lisa that you can use to get cool graphs out of. For example, if you, by the way, this close-up detail, you're supposed to look at it from far away. I guess you're far enough away. But then you can say how many levels of gray you want, and you can use that to define regions that are connected, workwise connected, and then if those regions are the vertices of a graph, and it's a planar graph, and you can see which regions are next to other regions. There's a graph based on cities in the United States and Canada, which has all of the mileage, exactly how long it takes to drive from one city to another. Here's one that's mathematical in nature, called a Ramanujan graph. This is a family of graphs that's some of the best known expander graphs, and expander graphs have a huge number of applications. So you can use the Stanford graph base to experiment with the Ramanujan graphs, which were invented by Stanford professors Ralph Phillips and David Sarnak and Lubatsky, and they actually hadn't actually seen many of their graphs until I had this software working to show them. They proved the mathematical theorem. So make graphs on games. Here shows all the knight moves that you can make in a chessboard that's 6 by 9 or any size of chessboard.
Lots of different ways to get graphs based on the games that come with boards, let's see. There's also in this about 5 years ago or so in this auditorium, I gave a lecture called Tori about Torreses, and it was when I was first thinking about some of these graphs that I was going to use as examples, and you see here's of course a lot of times we think of a graph algorithm, we want to try it out on cases that we can easily understand, like a grid or a cylinder or a torus, which is like a grid but wrapping around. And in that lecture that I gave about toruses some years ago, I thought what toruses is that are now, and the contents of that lecture are now encapsulated on page 45, where instead of having just a torus, which is like a 3 by 4 torus here, which you can imagine that these 12 cells are replicated over and over again in the plane, and it's the same as these 12 vertices replicated all over over the plane. It turned out to be the same graph, but you can also many more cases that don't fit into a square, like this one that has 13 vertices
and tile the plane other ways. And in that lecture that I gave, unfortunately, the videotape of that lecture, by the way, I loaned it to somebody, and I forgot who it was, and we've never gotten it back, so we can't put it online now. But maybe it's just as well, because at the end I had some problems I couldn't solve, and now the answer is in exercise 138. So as I was writing this up, it turned out there was actually a fairly simple solution to the problem that I was trying to solve that day. Okay. Now, quickly, I show you also the graph on page 44, which is cool. Any of you are musicians, because this has 24 vertices, one for every major and minor key, and then the easy modulation from one key to another, like from C major to A minor, or to C major to F major, and so on. These are this is a graph that it's called a musical graph. This graph was actually I found an abstract 2 or 3 years ago of a lecture given in England by Professor Robin Wilson, and so I wrote to him. The title of his lecture was "Beautiful Graphs," and so I said, "Well, that's a great title for a lecture. Can you send me the paper that's based on these?" He didn't have a paper, but he sent me the slides, and this was the first slide in his lecture on beautiful graphs, and he used this as an example in his Introduction to Graph Theory book written for undergrads at the Open University in England. Now, I stared at it for a while. I said, "Yeah, this is really a beautiful graph, but But is there any difficult problem to solve about this graph that I could use as an exercise, or is everything about this graph easy to answer?" And after a couple of hours, I couldn't think of an exercise that would give me a good excuse to use this graph in the book. And then I realized, oh no, that's the answer. This graph is a graph that all of the questions are easy on, and so it makes a great review question about all the concepts in this section. So what is the order of this graph? The size, the girth, the diameter, the independence number, the chromatic number, and so on. And it turns out that it's a good way to say, oh yeah, I know all these definitions, and by the way, it's not too hard to solve any of these parts of the exercise. But there is an unsolved problem about this graph, and that is is there a way to draw this graph into plane with fewer than 14 or whatever it is, 12 crossings, that's that I don't know how to solve. But okay, so I've shown you a whole bunch of cool graphs, but now let me show you an algorithm which you can generate graphs easily while you're sitting in a meeting with nothing else to do, when I was writing this, I happened to notice that there was a very simple algorithm. Let's see, where is it on page 29 here? A very simple algorithm that I'm going to tell you about. Four-step algorithm that's one of the, to me, was a good solution as to what kind of an algorithm about graphs can you put into the first few pages where you're introducing graph theory, because it's an algorithm that just talks about the most basic thing about graph, which is the degrees of its vertices. So let me this is one of the first problems, non-trivial problems to have been solved about graphs in the 1950s. You know what the degree of a vertex is. It's the number of neighbors that it has. And so if we have a graph like we can list all the degrees of the vertices. I told you Schwarzschild's graph, every vertex had degree 4. So okay, that's 4, 4, 4, 4, 4, 12 times. There are some sequences of vertices that are impossible. For example, if I have a graph, suppose the vertices are just 1, 2, up to n. Now, you know, these are the vertices. People often, almost always in a book, they'll call it V1, V2 up to Vn, but they're just writing a whole bunch of V's. They don't need to. You just, why not call it? So these are the vertices. So now, okay, so, but now they have degrees, and D1, D2 up to Dn, and we can choose the numbering in such a way that the degrees keep getting smaller. Okay. Now, the one obvious thing has to be true if there's going to be a graph that D1 can't be. What's the largest value D1 can have? How many neighbors can vertex 1 have? N minus 1. So first of all, one condition is that D1 has to be less than or equal to N minus 1. Has to be less than N. The second condition is that the sum of all the degrees has to be even. Does anybody know why that is true? It's because every edge contributes to the degree of its two endpoints. And so we're coming, so this is twice the number of edges. So, okay. Now, but that's not enough. Because you can have a degree sequence like 3, 3, 1, 1. It's the smallest, well, there are some using zeros that are, but anyway, let's suppose n is 4, and let's try to find a graph with degrees 3, 3, 1, 1. So vertex 1 has to be connected to 3 guys, so that's got to be connected to 2, 3, and 4. Oh, by the way, I draw my graphs in the book here with open vertices. I think that's cooler. It's used by in the book by Bondi and Murdy, Adrian Bondi and Murdy. A lot of books use solid ones, but I realize that their method is actually a win. So now, so 2 now has to be connected to 3 guys as well. Okay, fine. So 2 has to be connected to everybody. But now I'm supposed to have 1 and 1. You know, I'm out of luck. Okay. So all right. So there's something else going on here. So we say that a sequence of degrees is graphical if there exists at least one graph that has that sequence, and I'm going to show you this very beautiful, simple algorithm for which you can sit down, as I say, if you happen to be in a meeting and have some graph paper with you, then you have to have graph paper in order to work on graphs. If you instead of just doodling, you might also run through this algorithm because every different sequence of degrees seems to be a little bit different when you play the game. Suppose I'm taking now the sequence 5, 5, 5, 4, 4, 3, 2, 2. So I'm going to write this. I'm going to just put boxes here. 5, 5, 5, 4, 4, 3, 2, 2, and these are slots in which I'm going to put the neighbors of vertices. 1, 2, 3, 4, 5, 6, 7, 8. Instead of trying to draw the graph, let me just, I'm going to put the edges in here. So I'm going to list here the vertices at 1, the neighbors of 1, neighbors of 2, and so on up to the neighbors of 8. Okay. Well, now the algorithm I'm going to tell you about never appeared in English language before, but it appeared in the Czech language in a paper by Václav Havel in 1955. Now, this isn't Václav Havel, who you might have heard of as the president of Czechoslovakia. This is Václav Havel, the mathematician, who wrote this paper in 1955. And he wrote it in Czech, but he used some mathematical formulas in it. So I'm pretty sure what he said in the paper. I can't read Czech, but from the abstract of the paper and from the formulas and the sequences that occurred in the paper, I'm pretty sure he had this. And other people have referred to this paper, but they all gave a much more complicated algorithm than he himself did in the original paper. So it's much simpler than other books explain this process. And I want to show you a little game that you can play. So, okay, now you start out and you try to find the neighbors of 8 first. And what you do is you you always try to fill slots in the right hand column first. So I'm going to choose 8. The two neighbors of 8 are both going to be either 1, 2, or 3. But I'm not going to choose 1 because I want to keep this. I want to keep this diagram always non-decreasing order. So I'm going to match 8 to 3, and I'm going to match 8 to 2. But I didn't go from top down, but from bottom up, so that I wouldn't because otherwise it would have gone. It had a glitch in it. I don't want glitches. Okay. Now do the same thing with 7. 7 is going to fit here, and then so 7 is matched to 1, and then who else do I give 7? 5. Okay. So 7 goes. All right. And 6 is going to go here, here, and here, right? So that's 4, 3, and 2. 5 is going to go to 1. It's getting a little more interesting here. So 5 is getting to 1, sorry, and then 4 and 3. All right. The 4, let's put we got 2 4s here. That's perfect. 2 and 1. 3 is going to go to. You see, I got to fill this guy in. I don't want to send 3 to itself, but that's okay. I just make it so I put 3s here, and then great. 2, 1. Okay. So now we've got a graph with degrees 1, 2, 3, 4. Degrees 5, 5, 5, 4, 4, 3, 2, 2, and that sequence was graphical. If I had started out with 3, 3, 1, 1, it wouldn't work. Okay. Okay. Well, let's take another one. I was going to ask for a suggestion from the audience, but I don't have much time. We're running short of time. I don't want to go too far over. So let me do another one that I have canned in advance that'll show you a little more what's going on. 7, 6, 6. Oh, I'm sorry. 7, 6, 6, 4, 3, 2, 2, 1. No, that's not the one. 2, 2, 1, 1. Let's see. That's not the one I wanted to show you, though. Let's go to page. Let's see, 100 exercise 1. Okay, page 43. Yeah. Excuse me. First, want to do sequence. Here we go. Okay. Okay. 8, 6, 6. Okay. Here we go. So 1, 2, 3, 4, 5, 6, 7, 8, 6, 6, and then 6 4s. 1, 2, 4, 6. Okay. There we go. So here's 9 vertices, and I want to see if this sequence is graphical. Okay, so the question is, who are going to be the neighbors of 9 now? I've got to give 9 4 neighbors. So I want to use this column, so I put a 9 here, but now I can't use this column, you see, because I can't make one neighbor twice to 9. So I got to drop down to this column here, and I go here next for these 2 guys. And so these are 3 and 2. And then where's the next 9 going to go? 8, right. So the algorithm is just a little bit tricky. You have to, but which means that you know it's just enough to keep your mind occupied during this committee meeting, because you choose the rightmost column and you work bottom up, but then you have to go to the next group of things. You have to go to the next notch and then work bottom up at that notch, and so on. But well, let's keep on going. 8 has 3 guys, so that's pretty easy. Oh, no. 8 comes over here. here and here, doesn't it? Okay, so that's 1, 3, and 2. The order in which I put these doesn't matter. Of course, it's just going to be the neighboring here. So 7 is going to go here, 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 and here. So 7 gets, to 1, 6, 5, and 4. 6 has now got to find 3 neighbors, and I can put here, here, and here. So that's 1, 2, 2. 5 is going to go 1. 5 is going to go 3 guys, right? So I better fill it in as 1, 4, 3. Is it going to be graphical? 4, yes, no problem. 3, yeah, again we win. All right. Now, but you might want to see an example where we don't win. So that's this one. So what happens when it fails? And okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll let you do this to make sure so I make sure you understand what's going on here. 9 is going to be placed where? Up here with 1. Very good. 8, 3, 7 is going to be here. Okay. 6. 2. Okay. 5. 1, 4, 3. 4. 4 goes here, here, and here. It's okay. Made it. 2, 1, 3. 3. No problem. 1 and 2. Okay. And 2. Here is where I guess I've got to put it here. No, I'm stuck. I reduced it to finding a graph, on 2 vertices where somebody has a degree of 2. It can't be done. So that's Hello? Hi, is this what? Oh, yeah. Okay. Okay, so now I thought I'd have time to give a proof of this because the proof is actually not difficult, but instead I just refer you to page 30 because it's hard to follow the proof unless I had 10 minutes to really explain it slowly. But the main idea is that certainly if the algorithm succeeds, then you've proved it graphical because you've got a graph. But if it doesn't, you want to show that the mission was impossible. And the reason is that the strategy I'm using here, which is this sort of rightmost, bottommost strategy for placing everything, is the most conservative thing. The basic reason is an important property called majorization of sequences, like a degree sequence, and it occurs in many combinatorial algorithms where you say that one list of numbers majorizes another, and it means that the sum of the first guy is bigger. Okay, so let's say sequence A majorizes sequence B. That means that A1 is greater than or equal to B1, and A1 plus A2 is greater than or equal to A2 plus B1 plus B2, and similarly the sum of the first KAs is greater than or equal to the sum of the first KBs. That's called majorization. And it arises a lot, and I discuss it actually in fascicle 3 here. If I look at the index under majorization, I got a nice picture I can show you. Page 126. Page 126? No. Is that an error in the index? Oh, no, the main reference is page 58 to 80. Okay, so here's majorization, for example, of all the partitions of 12, all the ways to all sets of numbers that sum to 12. You can see some of them majorize other ones, like 531111 majorizes 522111, and it majorizes also 441111, but it doesn't majorize the guys over here. So anyway, these degree sequences are partitions of the total number of things that have the same sum, and what happens is that if one sequence majorize, if sequence D 1 through Dn majorizes D1 prime through Dn prime, and the first one, the D's are graphical, then so is the other one, the smaller one. So if a graphical sequence majorizes another one, the other one is also graphical. And so what we've done is we've sort of found a sequence so that no matter who I matched 8 up with here, if I matched 8 up, I might have matched 8 up with 6 and 3, or with 1 and 2, but I can match it up with any of the other two guys. But whichever one I chose, its what's left after I've deleted the 8s is going to be majorized by what I did. And so I'm making the safest assignment. So I can't be killing any graphical sequences by this method, and that's the basic idea of this algorithm. Okay, now and then you can actually see that you can randomize this in various ways. It doesn't give you a strictly random graph with these degree sequences, but if you ever need a graph that has certain degree sequences, there's an easy way to to generate it and then run your program on that graph. Whatever thing you're trying to play around with graphs, and you need a graph with certain degree sequences, you can get one easily this way. And there's lots of other modifications to this, and the exercises I show, for example, how to get a bipartite graph. If you want to say that you give the degree sequence of each thing in the first part and degree sequences of the vertices in the second part, it'll decide whether or not there's such a bipartite graph. There's many other things are known about these things, like how connected these graphs are and so on. Well, but I've reached the time when it would be good to start questions. Let me first see. Okay. Yeah. Right. So I can give more technical detail, but I'd rather wait for you to ask me questions, and then that'll suggest what else I can say that I know it will be of interest to at least one of you. So, are there any questions? And please,
Don, assuming one has a directed graph, and one wants to partition it into rank-ordered sets, which is to say, a set of cycles, is there a fast algorithm for partitioning or finding the rank in a directed graph?
So you have. So you're asking me. You're asking me to solve Condorcet's dilemma.
There are sets. Well, in fact, it is an issue.
Okay, so let me say that one of the databases in the Stanford Graph base is based on football scores from the I believe it's the 1990 season, and so I have in here all of the scores of the let me see. I can show you. an excerpt. But, let me see if I look up in the index. If I look up Stanford Cardinal, I believe I'll find a page where I can show you that graph. It's a directed graph, and then each. Okay, Stanford Cardinal, page 31. Okay, yeah. Let me show you this. Okay, but what you ask, I think, is a very, very difficult question. That's been, but games, it's a network. Okay. Beyond graphs, if you have anything, if the vertices here are decorated with additional data, it's called a network. So a network is a graph with plus something extra. So there's also there's, for example, one of these networks in the Stanford graph base is based on the United States economy divided into sectors. The complete flow of dollars from different sections of the economy to each other, as measured by the government in 1985. Well, this one is the games one comes from football scores, and there's an arc. Stanford to California value is 27. The arc from California to Stanford is value 25 because in the big game in 1990, Stanford won 27 to 25. Now, okay, so now the 1990 season was a very interesting season from the standpoint of your question because at the end of the season they try to say who is the #1 football team in America, and so you'll have these scores where some teams beat other teams, and then there are 3 polls. There's the UPI poll. Some coaches will vote for this, and then there's the Associated Press poll, and then there's another poll by the New York Times, I think it was, and each of those polls came up with a different national winner that year. So the question is, take the data from the Stanford graph base and figure out what is the answer. Who was the best college football team in the country? So, but this kind of ranking, I see all the Google people here in front of me, and I'm thinking PageRank. Ranking algorithms are certainly hot topics for a long time. But because paradoxical things can happen, and as I say, the different coaches came up with different rankings of the team. Now, one of the problems I'm going to have in Volume 4, based on these football scores, is to figure out a longest path algorithm, and I work it out here. In other words, you can say Stanford beat Berkeley, and then Berkeley beats somebody else, and then somebody else beats somebody else, and we get, and so let's see if I got it in here. So here it is. I said, starting team Stanford, other team Harvard. Okay, so here we go. Stanford beats the Beavers and racks up 34 points. The Beavers beat the Wildcats, so 35 to 21. So now Stanford is net ahead by 48. Wildcats beat the Lobos, and then the Lobos beat the Miners, and so on. Rainbow Warriors, Brigham Young. Finally, we get here. Yale, Harvard up 81 points. So Stanford over Harvard. Now, we don't allow intermediate teams to appear more than twice because, I mean, you can't have a loop. You could make this go to infinity. Okay. Well, now. This isn't the best. In fact, but the best score of Stanford over Harvard has been found, and the guy's announced it on the website, but he hasn't revealed his methods yet. But anyway, there's lots of cool graph algorithms that deal with ranking, but I don't know of a winning one. Other questions? Somebody in the back of the room? Nope. Front of the room wins. Okay.
About the algorithm that you described before on the that you drew, I was wondering, are the solutions unique, or there might be multiple solutions to the graph.
Oh, there's
And by unique, of course, I mean graphs that are not isomorphic to each other.
the solution to this degree sequence. Oh yeah. So no, you can see that there are lots of other solutions to this that would have worked. I mean, mainly.
I mean solutions that are not the graphs that are not isomorphic.
But and they're non-isomorphic. But there are interesting sequences that have only one solution. Well, to see if I can remember. For example, I think it's like. Okay. So let's try this. See if it's going to work. 7, 7, 7, 4, 4, 3, 3, 3. Now. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. You see what's going to happen here? 3, 3, 3, and then 4, 4. So this is going to have to. One is going to have to be connected to all the other guys, right? And so on. 2 is going to have to be 1, 3, 4, 5, 6, 7, 8, and 3 is going to have to be 1, 2, 4, 5, 6, 7, 8. And so therefore, I already know that 4 is, and this is without loss of generality, so not even isomorphism. So 4 has been connected to 1, 2, and 3, and 5 has been connected to 1, 2, and 3, and 6 has been connected to 1, 2, and 3, and 7 has been, and so on. So here we are. So 4 had better be connected to 5, and 5 to 4, right? So there are cases that are uniquely, where there's a unique thing, but that's very unusual. Usually there's many cases, and by the way, I wanted to mention that this algorithm that I showed you, the running time is proportional to the number of edges in the graph. But if you just want to see if the sequence is graphical, but you don't want to construct a graph, you just want to say yes or no, graphical or not, then there's actually a linear time algorithm using just the D's, where you just run through the D's and you do some very clever programming tricks, and then you know the answer. And the algorithm is this. First of all, given the D's, like in this case it was 8, 6, 6, 4, 4, 4, 4, 4. There's also you can compute with a very beautiful short program. You can compute the size of the columns. This is the 1, 1, 3, 3, 9, 9, 9, 9, 9. But for any sequence D's, you can find what's called the conjugate partition, the size of the columns. You can calculate that in linear time by a beautiful little method that I describe here in English. But it says K. Let me write it out in C for you. So K equals D1, J equals 0.
And then you say while K greater than 0, I probably do this as a for statement, it's better. J equals J plus 1, that's J plus plus. And then while K greater than D, K, can you read that? Dj plus 1, C of K minus equals J. There we go. So that calculates the C's in linear time. Zips through. Try to reconstruct it without, with your eyes, without looking at the sheet after a while. But it does exist, and you can figure it out. Okay. So you can find the C's. So once you got the D's and C's, then you can find what's called the Durfee square of a partition, which is the largest square that stays inside the partition. In this case, they're all 4 by 4s. It doesn't always happen, but in general, you try a 1 by 1, a 2 by 2, a 3 by 3 until you can't anymore. And the rule is that you must have D1 plus DK
has to be let me see, C1 plus CK minus K greater, I think it's this way. Yeah. The sum of the first KDs has to be less than or equal to the sum of the first KC minus K for K less than or equal to the size of the square. So the size of the square, S is the largest case where D sub K is greater than or equal to K. And so it's easy to determine S, and then you make this test, and in linear time you figured out whether the sequence is graphical. Now it's not easy to prove that this condition is equivalent to the algorithm, and in fact I found flaws in the proofs that I found in the literature about this, and so I had to work on that. In order to answer one of the exercises here, it took me several. I think it took me a couple of days longer than I expected it to. Yeah, here it is. So the answer on page 60 here. I had to go through all this long explanation here, and I think it does now constitute a correct proof. However, nobody has checked this yet. And so if you find an error in this, I'll pay you for it. I'm very glad to see somebody checking that, checking that deep, that I haven't made a mistake here, maybe just a typo. But I did work hard on this, and I want to make sure it's right, because in several textbooks they had proofs that actually didn't hang together when you looked at them, and I was hoping for to make it simple. This is as short as I could figure out how to do that condition. Which reminds me, as I'm working on this this section now, this this is going to be classical 1B. I spent altogether too much time 2 weeks ago on a problem that's a nice, clean mathematical problem. It's a recurrence that talks about how to if you have a Boolean function, you want to find a small circuit for it of a certain kind. You've got a method that, and the theorem in the literature was that this thing can't blow up, and I found a bug in the proof of that theorem, and I spent already 2 days trying to patch the bug, and I believe the theorem, but I can't find another way. So I wrote to the authors, a paper with 3 authors, and I haven't heard anything back. I don't know if they have, they treated my messages as spam or whatever, but it's a black hole as far as I'm concerned. So the authors should have a chance to correct the proof that they gave first, but I think it's a kind of a basic result in some ways. Although when my book is finally done, it's got to fit in about a half a page like this later. Or else, if there is no short proof, I'll have to hope that somebody does publish a correct proof so that I can refer to it in the literature. But right now, I don't know if that the result is correct. And so, if there's anybody here in the audience who wants to maybe work together, I don't want to work with just one person, but if you can find a group of 2 or 3 people who'd be interested in looking at this little mathematical problem, I could get together with you and explain to what the problem is, what I know about it, and the computational evidence that I have for its correctness, and then I can't pay you anything for it, but just say that it's something that you might find interesting. It won't be a big enough problem after you solve it to make a PhD thesis out of it, but it will be worth something for your own education at least, and this is an important enough result somehow in the structure of the theory of branching diagrams that somebody ought to settle the question. So I'm looking for volunteers on that problem. It arises all the time as I'm writing these, because I don't just quote stuff out of the literature. You know, I try to verify stuff that goes in my book, and I try to program everything before I present it as an algorithm, so that I know what it feels like to do it. Okay. Other questions? We're way in the back.
So if you start out with a graph of n vertices.
You can't hear.
Hello?
Yeah?
If you start out with a graph with n vertices, each vertex could possibly have a degree between 0 and n minus 1. So the possible number of sequences, sets of vertex sequences is n squared. Is there a formula to calculate, or an algorithm to calculate how many of those n squared sequences result in actual graphs, and how many are
Okay,
not?
yeah. How common is it for a sequence to be graphical? There was a paper, I just saw an abstract for a paper by Professor Liggett at UCLA last year, who discussed this question. Suppose you choose the degree sequence at random from different distributions, let's say the uniform distribution. Does it approach some probability? And unfortunately, the abstract, the paper didn't give the answer. But if you look up math sci, and the author was Liggett, L-I-G, he's a distinguished professor of statistical mechanics, Tom Liggett at UCLA, and he wrote a paper about that question last year, but I don't remember the answer. I don't know the answer, but I think that it's pretty common. That is, if you just roll dice and get it, you probably will find that it's graphical. What? Oh, I'm sorry. That was all. That was in the abstract. Yes, it said yes. It either goes to 0 or approaches a half, or some value in between. This is right. The sum has to be even. Yes.
I was wondering if there's any interesting generalizations of this problem, of the problem of for example, the hypergraphs or something like that.
Okay. Yes. One of the generalizations that, okay, in fact, there have been many, but I didn't go into too many into here. So I generalized it, as I said, to bipartite graph, which is also equivalent to directed graphs. If you, in a sense, it's but the very, very well-known problem of a matrix of zeros and ones, and you want to know the row sums and column sums of that matrix, and so there's an algorithm very much like algorithm H, with just a few changes will solve that problem. But then some far more far-reaching ones have been to say, well, now you want to graph. Okay, so I believe it's an unsolved problem. Yeah, it's an unsolved problem. Given a degree sequence, is there a planar graph with that degree sequence? Open question. But is there a self-complementary graph with that degree sequence? Now, a self-complementary graph is a graph that's the following: is imagine that you have n points, and each one is either joined by a red edge or a green edge. So then the red edges define a graph which have half of the total number of edges, and the green edges also do, because the graph is self-complementary. If you change the colors, you still get an isomorphic graph. The graph formed by the red edges is isomorphic to the graph of the green edges. So that's called a self-complementary graph, and I have several exercises about self-complementary graphs because that's another elementary topic to discuss. Well, a intricate extension of this algorithm H was found by Kleitman and Dalun Wang. Danny Kleitman at MIT, and Dalun Wang was one of his students, and then Wang went into I think he's now working on Wall Street in finance and making a lot of money instead of doing graph theory. But he proved this quite delicate theorem about to characterize when a sequence is possible to make a self-complementary graph from. And there are other. They had another paper as well. No, I'm sorry. That wasn't Darwin Wang. That was some guy named Clapham in England. He and Kleitman and Wang proved the theorem about can you make a graph that is like 4 connected or 5 so you discuss the connectedness of the graph from this degree sequence. So there are generalizations like that. But to me the most interesting one is just the elementary problem itself and the fact that it had nice proof. I did this afternoon look up in Math Sci. I gave the keywords degree sequence, and I got 186 hits of papers written that had that in the title. And so and there are many other papers on the concept that didn't happen to use the word degree sequence in the title. So there's a huge number of people investigating questions like this, and some of the questions are more interesting than others. But with graph theory, you never run out of questions. Well, thanks for staying an extra half hour late, and have a good, cool summer.